Okay. Welcome to Bacteriological Water Monitoring. So let me know as we go along here if anybody has any issues with seeing or hearing, or we have any other issues. Sorry. Okay. So I'm Eric Admin, Sno-King Watershed Council. We're a all-volunteer nonprofit organization working to protect local creeks and natural areas. We're also part of a larger organization called Global Water Watch, which trains volunteer water monitors in a number of different countries around the world. This is an example of one of the places that Global Water Watch has worked and done bacteriological monitoring workshops over in Africa. They did some workshops and worked with some groups in Kenya. What we're going to be going over today is we're going to briefly review the general topic of water monitoring and what, why, who, where, when, and how. We'll talk about some basic concepts of what water, watersheds, and water pollution. And then we're going to primarily spend our time learning Global Water Watch techniques for bacteriological monitoring. So we've talked about this in the introduction class, but what is water monitoring? It's a regular systematic assessment of conditions in a water body, oftentimes a creek. We might do it for different reasons. We might want to know what's happening. Are the conditions good for fish? Are they good for people? Are they changing over time? There could be a variety of different reasons why we want to monitor the water. It's done by volunteers and it's done by professionals. It's done by academics. It's done by a variety of different people for different reasons. It's typically done at a site that you've selected using specific criteria to make sure that that site is giving you some useful information. And we're going to get into the how of bacteriological water monitoring this evening. So just reviewing some basic concepts. A watershed, again, is an area of land that drains to a water body, typically a stream. And so everything that happens in that watershed affects the water quality of that water body. Another concept is something called stormwater, and that's water that falls on the landscape and runs off. And typically it goes into storm drains, and those ultimately go into a stream. Now, in an urban setting, it's going to run off a lot faster than it's going to in a rural setting, and it's going to raise the level of the streams a lot faster. There can be a variety of different pollutants that are in it, including some things like tire particles that are toxic to salmon. And so that's caused some issues with urban stream mortality syndrome for our salmon, among other issues. So stormwater is really one of the hugest topics when you're talking about water quality and you're talking about watershed health, stream health, salmon, water quality. Things that run off in stormwater are one of the biggest factors. There are some things that people can do themselves to reduce water pollution, and we've talked about some of these before, including rain gardens, which are things that will filter stormwater before it gets into a stream. Restoring stream buffers so that water that runs off goes through a buffer before it gets to the stream, and the stream is shaded so the water is cooler. Picking up pet waste to reduce bacteria levels of running into the stream. Fixing oil leaks so we don't have other toxins running into the stream. Similarly, avoiding fertilizers and chemicals prevents those pollutants from getting into streams, and doing things to limit stormwater runoff. Okay, we're going to get into the nuts and bolts now of bacteria monitoring. So the reason why we do bacteria monitoring is we want to know, is it safe for you to do something in that stream? And if the bacteria level is too high, then it might not be safe for you to get in contact with the water in that stream. Bacteria are single-celled organisms. You can't see them. They're everywhere in our environment, including inside of us and on our skin. They are necessary for life. They're necessary for us to live. They're necessary for life on our planet. So they're really essential organisms. They're involved in converting things from one form to another. So they kind of help break things down and move things from one phase to another. They're also related. And so the families that we're concerned about are ones that are called coliform bacteria. And specifically, we're interested in E. coli, which is a particular type of coliform bacteria. And even within E. coli, there's multiple types of E. coli. There's one specific one that's pathogenic that we're primarily concerned about. So E. coli is, when you find E. coli, which is the testing that we're going to learn this evening, shows you how to find E. coli, or it will give us a color indicator when we found E. coli. That is indicative of fecal coliform contamination in water. When you find that, it also means there could be other dangerous organisms. This is one of the biggest issues with contaminated water worldwide. And we're really lucky in our area that we generally have access to safe drinking water. A lot of places around the world, people get their drinking water out of a stream or a river or a lake. And so they don't have quite as good access. And so if you had bacteria contamination, it could really cause an issue for them. That's the particular strain of E. coli, which is the one that's most concerning. So there's a number of different sources of bacteria in water bodies. One is pet waste. So you may have seen more signs and more of an emphasis on people picking up after their pets. And in fact, in Kirkland, they've gone through a number of different initiatives to try to limit the amount of dog poop that is getting left in parks. And so one of the things they did was this experiment in Juanita Beach Park, where they would put little flags where people had not scooped their dog poop. And then they would talk to people who hadn't scooped their dog poop. And their outreach campaign, I think, was effective in reducing the amount of dog poop that wasn't being picked up. Another place that bacteria could come from to get into a stream or water body is from what's called a failing side sewer. So in a house, when you run the water into the sink or you flush the toilet, it goes into the sewer system. And to connect to the main sewer line, there's a side sewer. And sometimes these, especially in older properties, these are made of like concrete pipe, and maybe a tree root grows into it or the ground shifts or whatever. So these things can fracture and you can start getting sewage seeping into the ground. And this can cause bacteria contamination in a stream. So this is something that was happening in a watershed in the Seattle area, Thornton Creek watershed. They found that they were having high bacteria levels and traced some of those in a particular reach of Thornton Creek to failing side sewers. Another source of bacteria can be agricultural animals that are allowed to just walk in the stream. And so they don't discriminate about where they leave their waste. So if they're allowed to just walk into the stream, they may leave their waste in the stream. So that could be another source. Another example locally is at UW-Bothell. They have a gigantic crow rookery. And so they have tens of thousands of crows that return there every night. And so, as you would expect, they poop a lot. And so the bacteria levels are, if you look at North Creek, which flows through that rookery, if you look at upstream and downstream of that rookery and compare, that's another source of bacteria. Another thing that correlates with high bacteria is high turbidity. Turbidity, dirt particles in the water provide kind of an attachment point for different contaminants, including bacteria. And also there can be bacteria in the dirt that's on the sediment in the bottom of a creek that gets stirred up when the water is high. So like when we've seen some high turbidity events on the creek that we live on, Little Swamp Creek, we've also found that some of those correlate with very high bacteria levels. So how do you measure bacteria? In using the Global Water Watch techniques, they emphasize that you want to be consistent about how you do it. You're going to do it consistently using the same method, going to the same place, essentially trying to do it at the same time of day. And if you use consistent techniques, you can come up with credible data. The measurement unit is what's called a colony forming unit. And so you get colony forming units by collecting samples, giving them a little bit of food called media, incubating them, and then they grow into colonies that are big enough that you can see. So each of those blue dots on that, what's called a petri dish, represents an E. coli colony. And what you do is you count how many of those colonies you've found in a 100 milliliter sample. Normally, the sample of water that we collect is about anywhere from 1 to 5 milliliters, typically 1 or 2. And so you'll do a little bit of math after you go through this process and you go, okay, well, I collected a 1 milliliter sample and I found 5 colonies. So if there was 5 in 1, that would be 500 in a 100 milliliter sample. So that would give me 500 colony forming units, or CFUs. So that's kind of the vocabulary that's used when you're talking about bacteria levels. Global Water Watch in their training set some standards for bacteriological monitoring, and they have this stoplight graphic representing safe, be cautious, definitely unsafe. And so this is kind of their worldwide standard. What you find is that different jurisdictions have different standards. So for instance, in Washington state, we have stricter standards. So this is a section from what's called the Washington Administrative Code, which is Washington state law. And so this is stricter than national standards and it's stricter than Global Water Watch standards. There used to be a number of different levels, but a couple of years ago, they changed what they set the safe level at. And so essentially what they're saying is you want to have it less than 100 colony forming units in 100 milliliters to be considered safe for contact. This plays into another concept that I want to make you familiar with, which is what's called a listing, an impairment listing. So under the Clean Water Act, Section 303D, they create a list of impaired water bodies, and that's administered locally, like in Washington state, by the Washington State Department of Ecology. So somebody who's collected data on water quality impairment can submit their data to the Department of Ecology to get a water body on this 303D list. Usually the entities that submit that data are like local jurisdictions, but they could also be an academic institution or even a volunteer group. So once something is on this 303 list of impaired water bodies, then the local jurisdiction or whoever has control of that water body is tasked with coming up with a water quality improvement plan. And then as part of that water quality improvement plan, they establish maximum levels that they don't want to find. They want to find levels of whatever the contaminant is below that level. So a water body can be listed for bacteriological contamination. It could be listed for chemical contamination. It could be listed for low dissolved oxygen. It could be listed for high temperature. But a number of creeks in Washington state and in our local area are listed on the 303D list for impairment due to bacteria. And in fact, the creek that Little Swamp Creek, and which is tributary to Swamp Creek, are both listed for bacteria. All right, let's talk about the specific steps for bacteria monitoring. So this is what the pieces of equipment look like that we're going to use for our bacteria monitoring. So those dishes are called Petri dishes. They're just plastic dishes that have a bottom and a lid, and the bottom is coated with a particular coating that when you put a water sample in there and you let it sit for a period of time, typically about a couple hours, it will gel, so it will harden up. And the purpose of that is that when you've put you put your sample in there, if it stayed liquid, you would never be able to count the colonies. So essentially it makes the colony grow in one place so that you can count the colonies. So you've got Petri dishes. You've also got what's called medium. We're using a particular technique called Coliscan Easy Gel, and the medium is essentially a food for the bacteria. So you collect a water sample and you put it in that little container, that little jar, and that's where you'll put your 1 to whatever milliliter sample, and then you'll subsequently pour it into the Petri dish. So that gives the bacteria some food to grow. You're going to use something called a pipette, which is like a little something you can suck up water with. So that's what you're going to use to collect your sample. A thermometer, so you can record water temperature, because there's a correlation between water temperature and bacteria levels. So typically you find that in warmer water, you have higher bacteria levels. Colder water, you have lower bacteria levels. Bacteria generally like to live at about body temperature for us. And so another piece of equipment that we use is the incubator. And once we've collected our sample, we're going to put it in that incubator and incubate it for 30 to 48 hours at 29 to 37 degrees Celsius. So those are the materials. So step 1 in doing bacteria monitoring is get your materials ready. A couple other items that you're going to use is you're going to use a data sheet. And then when we collect our samples, you either transport them not on ice for less than 30 minutes before you plate them and incubate them, or you can transport them for up to 3 hours on ice. So typically in the materials that we have a little insulated lunchbox and an ice pack, so that when you collect your sample, you can transport it on ice, so you don't have to worry about immediately plating it when you've collected your sample. So a couple other steps that you do before you incubate, you're going to take these Petri dishes and you're going to label them, and you're going to tape them so that you can open it, because you don't want to introduce unnecessary or extra contaminants in there. So you want to keep it closed up until you're actually going to pour your sample in it. And then once you've poured your sample, you want to seal it back up. So typically we do that by taking a piece of Scotch tape and making what we call a hinge on one side and what we call a tab on the other side. The tab is just a piece of tape that you can peel back a little bit enough to open the Petri dish. So that's another step that you're going to do. And then you're going to label your Petri dishes and label your media. So for example, if you were going to go out and monitor one site, one thing that you'll learn here is we collect 3 samples per site. We call them 3 replicates. So we want to have a way to label those to make sure we don't accidentally put our sample that we've just collected back in the same container where we just put another sample. So we'll label them. If it's just a single site, we might label them, like I monitor Little Swamp Creek, I might label them LSC1, LSC2, LSC3. But if you monitor multiple sites, then obviously you want to just label all your media containers so that you keep track of what samples you've taken and where they've come from. So you've prepared your materials, you've got everything ready to go. So now you're out at the site and you're going to collect some samples. So first thing you're going to do is unwrap that pipette. Then you're going to collect a sample, and you want to do it where you're not disturbing the water. So you want to do it away from yourself. If you're in a moving water body like a stream, you want to collect a sample either upstream from yourself, or if you're standing off to the side of the stream on the bank, then collect the sample where you're not disturbing the water. You also want to make sure that you're below the surface of the water, but you don't want to be touching the bottom. So that's pretty straightforward. You'll collect your sample and then you'll put it back into the media bottle and cap it. And then you're going to transport it back to where you're going to plate it. So I'm going to switch over and we're going to watch a video from Alabama Water Watch on collecting samples.
Welcome to the Alabama Water Watch instructional video series. This video will show the proper method for collecting water samples used to determine the number of bacteria in the water body. This is the first step in a 3-step process. The second and third steps, plating the samples and determining results, are covered in their own separate videos. For each site being tested, you will need a cooler with ice, 3 media bottles at air temperature, a sterile pipette, and a thermometer. Label your media bottles by site and replicate. If you sample multiple sites, be sure to use separate data sheets or keep record of monitoring site and bottle numbers that are grouped in sets of 3 replicates. For example, if you have 2 sites, you can number the replicates at the first site as 1A, 1B, and 1C, and the replicates at the second site as 2A, 2B, and 2C. Upon arrival at the site, measure the air and water temperatures. For instruction on how to measure these temperatures, please watch the video called Water Chemistry, Air and Water Temperature. Once you are ready to sample, unwrap a sterile pipette from the bulb end and avoid touching the tip of the pipette with anything except the sample water. Fill the pipette with sample water. Be careful to not disturb the bottom of the stream. Carefully squeeze the bulb and expel excess water to the desired sample volume. 1 milliliter sample volume is recommended and is usually sufficient. Be sure to use the same volume for each of the 3 replicates and record volumes on data forms. Remove the cap from the media bottle and hold it without touching the inside. Squirt the sample water into the bottle of liquid media without placing your hand or face over the open bottle. Cap the bottle securely and place inside the cooler. Repeat these steps until all 3 media bottles are inoculated with water from the same spot. Keep in mind that media must be plated within 3 hours of collecting the sample and should remain on ice and out of direct sunlight at all times. Thanks for watching. If you have any comments or questions, give us a shout.
Okay, I'm just going to pause right there and just ask if anybody has any questions so far. Nope.
I have a question.
Sure.
So in my water quality class that I'm taking, we were basically told to use Collisure medium, which turns magenta if it's in the presence of coliform bacteria, and it fluoresces under UV if E. coli is present. Will we have to do that specifically, or is that not like the procedure that we will be using?
So the procedure that goes with the Global Water Watch technique is using the Coliscan Easy Gel, but there's a lot of different techniques you can use for identifying E. coli bacteria. So it sounds like the water quality class you're taking, they use a different method. The method we use is this Coliscan Easy Gel. We're actually, Global Water Watch is actually working right now on comparing a different type of sampling method, where instead of using the Petri dish and the media and all that, you actually use it's like a paper card, and you just put your sample on the card and then incubate the card and count the bacteria directly on the card. So there's different methods, but currently the method that we use from Global Water Watch is the Coliscan Easy Gel.
I have a question, Eric. Actually, two. One is the video recommended putting it on ice immediately after you take the sample. The data sheet suggests that if you're going to plate it within 30 minutes, that it doesn't need to be iced. Is that okay to do it that way?
Yeah.
Okay. And so you plate it, but then you have to leave it out for maybe an hour, hour and a half before the gel solidifies and you can put it into the incubator. And so that's still okay, right?
That is okay. And we will see a video on plating and incubating, but just to give you an update, we've gotten an update on techniques subsequent to when that video was made. And so what we've moved to now is actually plating and putting the sample directly into the incubator, as opposed to putting it gel first. So
okay, well, we'll see that when it comes. Second item was, I would the recommended, or the limit listed for coliform for recreational activities was 100 CFUs. 100 CFUs per 100 milliliters. And I was wondering, I was looking at that as a 3-month geometric mean with a 300 maximum. Have you seen that anywhere?
I haven't seen it as a 3-month geometric mean. Technically, though, the sampling is supposed to be based on a geometric mean.
Right. Well, I was looking at Washington State guidelines. I think I'm not sure what the number was, but I was seeing a 300 CFU per 100 milliliter single sample maximum. But I'll send you the reference on that.
Okay, sounds good.
Okay, thank you.
Sure.
Will you be covering where we get the Petri dishes and the equipment and the cooler stuff, or do we provide it?
If you're monitoring with us, then we will provide it.
Okay.
Yeah, we have a grant from King County right now. It's from King County Waterworks, provided by the Wastewater Treatment Division, and that pays for our monitoring supplies.
Okay.
All right. Is everybody ready to move on?
Yep.
Okay. Okay, so that was collecting samples. The next stage after you've collected the sample, so we went out to the site, collected our samples with our pipettes, put it into our media, either transported it back less than 30 minutes, not on ice, or greater than 30 minutes, but less than 3 hours on ice. Now we get back to where we're going to do the plating. So we're going to use our incubator, and ideally you want to have your incubator already warmed up, although that's not essential with the incubators we're using now, because they warm up pretty quickly and they go to a programmed temperature. When you open up the Petri dish, again, you don't want to just leave it sitting open. You just want to open it briefly, just so you can pour the media in with your sample. You want to swirl it around just gently a little bit on the flat surface that it's on, so that it covers the whole bottom of the Petri dish, but you want to try to avoid sloshing it up on the side, because what you'll find is if you get colonies that are growing up on the side, they can be hard to count. And then you're going to place it right into the incubator and let it start incubating. So we'll watch a video now on plating samples so you can see it in action.
Welcome to the Alabama Water Watch instructional video series. This video will show the proper method for plating water samples used to determine the number of bacterial colonies in a water body. This is the second step in a three-step process. The first and third steps, collecting the samples and determining results, are covered in their own separate videos. Prepare your petri dishes by taping the top, the larger piece, to the bottom, the smaller piece, on one side of the dish. Keep the dish closed as much as possible to avoid contamination. Label the plate lids with labels that correspond to the inoculated media bottles in data form. Lift the top of the petri dish just enough to pour the contents of its corresponding media bottle into the plate. Do not slosh the media onto the sides or lid of the plate. Record the time you plated your sample on your data form next to incubation start time. Be sure to shield the sample plates from direct light. Leave the plates undisturbed until the media has gelled, usually about 1 to 1.5 hours. After the media has gelled, use another piece of tape to secure the untaped side of the dish. To prevent condensation from dripping onto the plates from the lids, turn the plates over and place them in the incubator. Incubate plates between 29 and 37 degrees Celsius for 30 to 48 hours. Thanks for watching. If you have any comments or questions, give us a shout.
Okay, I'll stop again just to clarify a couple things. One is that in the video they showed covering them up and leaving them out for 1 to 1.5 hours. As I mentioned, generally we just, once we plate them, we put them right directly into the incubator. And the other thing is they talked about flipping them upside down. So if you think about it, your sample is in the bottom of the dish and it's in the incubator. In some cases that can generate some condensation that can run down and start to dissolve the sample, the gelled sample. So usually what we'll say is after a brief period, you can flip them over so that that doesn't happen. I've found that that experience is variable. So like in my particular case, I don't really seem to have issues with condensation. I just plate them, put them in the incubator and let them incubate, and I don't have condensation issues, but some people have reported condensation issues. So if you discover that, then you can flip those incubating plates over to avoid that issue. Any questions so far?
So Eric, sorry, just wanted to make sure that the not needing to solidify versus, solidifying, can you do it either way, or is it now recommended that you don't solidify the plates before you put them in the incubator?
You can do it either way. We were just finding a lot of monitors were reporting variable time, like sometimes taking much longer than 1.5 hours to solidify.
Got it.
So it was just making people wait around a long time before they put them in the incubator. So you can still do that. And if room temperature at your environment, they seem to solidify fine, then that's fine. But it's also okay to just put them directly into the incubator.
Eric, one of the things that happened to me this past year is that Micrology Labs was producing defective plates that had bad coating on the bottom and it never solidified. I don't know if that was part of the problem that others had too.
There were some issues with Micrology Laboratories, which is the supplier of the Coliscan Easy Gel bacteria monitoring supplies. Trying to make a long story short, essentially the company changed ownership, I think during the last year to two, and they had some quality control issues initially with what they were making. So other Global Water Watch and Alabama Water Watch programs were having some issues. At this point, I believe the issues have been resolved. I haven't had any issues recently with it, but we did go through a period where we did have some issues with our supplies. All right, thank you. I'm going to get back to our presentation. So that was plating the samples. So we've collected the samples, we've plated the samples. Now we're going to incubate them. So we're going to incubate them again we're measuring in Celsius, so 29 to 37 degrees Celsius, which the upper range is close to body temperature, and about 30 to 48 hours to give those colonies time to grow. And then there's the optional flip them upside down. Then the next thing you do is once you've incubated them, then you're going to count the colonies and determine your results. And so there's some particular ways to do that, to make that easier. So I'm going to share with you a video on determining results.
Welcome to the Alabama Water Watch instructional video series. This video will show the proper method for determining the results of incubated water samples. This is the third step in a three-step process. The first and second steps, collecting the samples and plating the samples, are covered in their own separate videos. Remove plates from the incubator, being careful not to spill any liquid. Be sure to record the incubation period, which is optimally between 30 and 34 hours. When counting the number of colonies, it is helpful to use a white sheet of paper to split the plates into quadrants. Count all blue to purple colonies on each plate as E. coli. Do not count very small or pinpoint colonies smaller than the period at the end of a sentence. Count or estimate the number of all pink to dark red colonies on each plate as other coliforms. Estimates of more than 100 colonies should be reported as abundant, and estimates of more than 200 colonies should be reported as too numerous to count. This sample should be recorded as too numerous to count. If colonies appear as a ring around the edge of the plate or as one large blob, count as one colony. Record both the number of E. coli and other coliforms on the data form. The bacterial concentration in 100 milliliters will automatically be calculated in the Alabama Water Watch database. To calculate the bacterial concentration by hand, divide the number of E. coli colonies counted by the sample volume, then multiply by 100. Kill the bacteria by pouring about a teaspoon of undiluted bleach into the dish. Let stand for about 15 minutes, then dispose of with household garbage. Thanks for watching. If you have any comments or questions, give us a shout.
Okay, I'll stop again just to clarify one thing and then see if anyone has any questions. In terms of the incubation time, they made a misstatement in the video where they said 30 to 34 hours, so it's 30 to 48 hours. And otherwise, that's essentially the process of counting the colonies. The other thing to comment on is we're primarily interested in the E. coli. We're not so interested in the other coliform. I mean, we count or estimate them, I think, to make sure that we've run a valid sample, that our process is working, because if we only found E. coli and we didn't find anything else, it would be kind of something might be wrong with the process. But we don't really do anything with that data. The other coliform, aside from it, will show up in your global water watch graphs. But we're mainly interested in the E. coli numbers. Anybody have any questions about that?
Eric, what was that dilution calculation they had again? I kind of missed that. It was count the number of colonies, you divide it by the dilution sample, then multiply it by 100.
Yeah, we're going to go through that. We're going to do some counting exercises. All right, so now we're going to go through some exercises of counting. So take a look at this plate, and you can see that some of them look dark blue and some of them look sort of more pinkish, purplish. So it helps to sometimes put the plate on a grid or impose a grid over the plate. Sometimes I might draw a grid either on a piece of paper or on a Petri dish lid and put this on it so it helps subdivide it, especially when you're trying to count like the other coliform. So we're going to count up our blue. So we've got 7. So 7 E. coli, and our sample volume was 1 milliliter. So there's our formula, is the number of E. coli divided by the volume times 100. So in our case, it's 7 divided by 1, which is 7 times 100. So 700 is our result. And then we're going to interpret that result and say, well, what does that mean? The other thing we're going to do is we're going to count up all these other coliform bacteria as well as we can. And so in this case, we counted 45 in a 1/8 fraction of the dish. So multiplying that by 8 is 360. And then because our sample was 1 milliliter and we're comparing it to 100 ml sample, we multiply that by 100. So 36,000 other coliform bacteria. So there's a couple of questions down there: good source for drinking water and good for recreational beach. What do you guys think? Would that be good for drinking water or for a recreational beach? Feel free to unmute and chime in.
Neither.
Yeah, no, that's fairly contaminated. I've seen worse, but you definitely don't want to be in that water. So we compare it to our standards. By Global Water Watch standards, it's not safe. And by Washington State standards, it's definitely not safe. So we'll do a couple more exercises. So in this case, what's different is that our sample volume is 5 milliliters. We still have 7 E. coli. But in this case, because our sample volume is 5, our number is going to be lower because we're dividing that by 5 before we multiply by 100. So in this case, it's 140. So according to Global Water Watch standards, that's okay. According to Washington State standards, that's not okay. All right, so let's do an exercise. Let's have you guys go ahead and maybe unmute and go ahead and count and call out how many colonies you see in this sample.
12.
12.
13, I see 13. 1, 4, 5, 6, 7, 8, 9, 10. I get 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah.
12. I think I see.
We
Okay,
get
I see.
12.
So if there's 12 in the plate, then, and our sample is 1 milliliter, what's the level per 100 milliliter?
1200.
Right. So we have 1200 CFU, colony forming units, in 100 milliliters. So definitely not safe.
Bad.
Okay, how about this example here? How many colonies do we have on the plate?
6.
6.
6.
Yep, I count 6.
6.
Now, if our sample is 0.5 milliliters, then doing our math, how many would that be in 100 milliliters?
1200
again.
Yep, 1200 again. Okay, so here's one.
He should have showed that.
What's that? Oh, they should show the, yeah,
I just think that might be.
the math.
Yeah. Mhm.
You're right.
Why it's 0.5 would then be 1200.
Yeah, you're right. It's because you're dividing by 0.5, which is essentially like the same as multiplying by 2. But you're right. I should show that math. So that's basically how you do this. So you go through your different, you count your colonies, and then you do the math according to the formula. The E. coli equals E. So your E. coli colonies divided by the volume times 100. And so you go through that math process, and that's how you come up with what your count is for CFU. So now you've gone through your counting and you've kind of interpreted your results. You're going to record it. This is an example of what the data sheet looks like that we use to record our results. And one of the things on this, there's a incubation. On the header is kind of all the information about you. There's some check boxes on was there enough water. You're going to record the air and the water and your sample size. Then the incubation time that you list is the time that you plated. So that's essentially when you start the clock for your incubation time. And then you're going to record the temperature, the amount of hours that you incubated it. The media has an expiration date, so you're going to record that to confirm that you're not using expired media. You'll indicate if you plated it on site, which we almost never do, and then how you transported it. And then after once you first incubate it, you record all that stuff. And then after you're done incubating, you can record the incubation period and count your bacteria.
I have a question.
Sure.
So if your media is froze, if you've taken it and frozen it before its expiration date, but then you're using it from the freezer after the expiration date, do you note that, or?
No, it's supposed to be stored frozen. So even if you've been storing it frozen, if it's past the expiration date, you can't use it.
Oh, okay.
And then the cleanup process, the process that they recommend is use a little bit of bleach to kill the bacteria and then dispose of it. I've had some other monitors say that they seal it up and dispose of it. That's one of the reasons, in either case, that's one of the reasons why we're looking at some new techniques that might use less materials and be less, putting less bleach into the system. But that's the current system that we use, is cleaning it up with bleach. Okay, so now you've gone through your process, you've collected your data, you've counted it, now you're going to do something with it. So you do what we call interpreting and presenting your data. So think about what it means, and then how do you want to use that information? Another thing that you can do is you can compare sites within a given watershed that might help determine where you want to monitor, or it might help you determine what are some actions you think need to happen in that watershed. And the question we're asking is, my water body's water quality getting better or worse, and why? So here's one way that you can present and interpret the data. So this is a graph from the Global Water Watch system, and it shows different high bacteria levels at certain particular times, typically associated with the summertime on this particular site. So in this case, on this site on Little Swamp Creek, on the headwaters of Little Swamp Creek, which is in Bothell, we kept finding these high levels. And so we got the city of Bothell to investigate, and they still haven't really resolved it. They've got some potential ideas about the source, which may be a historic sewage lagoon associated with an agricultural site. But basically, you can show that you're collecting this data systematically, and you can use it to encourage a local jurisdiction to take some action. So that shows you how often that particular water body is above Washington state standards. Another thing you could do is you can turn your data into a poster. So here's something that Lake Forest Park stream keepers used in showing water quality in Lion Creek and Mackler Creek and the impact of stormwater, especially what we call the first flush, so the first heavy rain. So they use this at, there was a pre-COVID and probably maybe post-COVID here in a bit. They've had a sort of a green festival in Lake Forest Park, and they used this poster at a station that Lake Forest Park stream keepers had set up to raise awareness about the streams. Another case.
Hey, Eric.
Yeah.
Sorry. I know that these are just pictures, but it did raise a question I had. How long does the E. coli remain purple? I mean, let's say if I needed to count it at a different time, do you know what their how long I could wait before you have to make a count for sure?
Well, so you're supposed to count after you've let it incubate for the given period.
Oh, I see. Yeah.
So 30 to 48 hours, you want to count it in that window. But I've had dishes that sat around for a while after the fact, and they don't change color again. They just continue to grow.
Yeah. What if you stuck it in the freezer or something? I know that's not what we want to do here, but I'm just thinking that if something came up and all of a sudden you had to go somewhere, would that be acceptable?
I don't know that. That's a good question. Would you be able to count it?
Yeah.
I haven't really had that come up. I have kept samples in the freezer sometimes when I found some really remarkable results, and I wanted to share it later with some volunteers to show it to them. So you can do that.
Okay.
I don't know that I would. I don't know how that would affect your count.
Yeah. Okay.
Here's another example of what you can do with data is you can, if you have multiple sites within a given watershed, you can collect data simultaneously at those sites. So this example is from Alabama, but we had a local example of that in Seattle in the Thornton Creek watershed. They started doing a bi-monthly simultaneous data collection event on different sites throughout the Thornton Creek watershed. And they did it the same day of the week and the same time of day, twice a month at multiple sites. And the purpose was they were trying to find out where was a particular site or where were the highest levels of E. coli so they could correlate those and maybe find a source. And so by doing that process, they ultimately did find a source. They worked in conjunction with Seattle Public Utilities, who helped them design this citizen science experiment. And they found that an apartment complex had a side sewer that had been incorrectly plumbed into the storm sewer. So that was one particular source they found. Another thing you can do is you can bring it to people's attention so that they will post a warning if you find a water source that's especially dangerous. This is a case where Global Water Watch was working in Kenya, and they had people collect samples, and they drew a map of their watershed on the floor, and they brought people's data sheets in and put them on the floor to kind of represent the watershed. And then they translated that into actual watershed map, so people could see where the hot spots were in their watershed. Another way this data is used is in something called the swim guide. So there's a number of different water keeper groups around the country, and they maintain an app called the swim guide. So people would maybe consult this guide before they go swim at a beach. And in some cases, the data could be collected by volunteers or it could be collected by agencies, but they can use that data to identify high bacteria level beaches. And here's a poster from Global Water Watch Mexico, where they were just comparing a number of different sites and sort of giving you the like happy face or the frowny face, depending on what they were finding with E. coli at different sites. So there's lots of different ways you can put your data into action. So that's it for us. I always want to say thank you to all the different individuals and groups that help us put our program together, and to all of you for the volunteer work that you do. And I'll stop the recording here and see if anyone